Problem 5-28, and this one is also a perpetuity problem. And we are starting out with an investment that's going to pay $70 in 1 year, but as a bit of a twist in this problem, the payments are going to grow after year one by 5% forever. So the annual payments are not going to be the same. We're going to start at $70, and that $70 is going to grow each year by 5%. So part A starts off fairly basic. What's the present value of that first $70 payment? And we're going to assume a discount rate of 9%. So with this, we could just use the basic present value formula. We would take 70 and we would divide by 1 plus the discount rate, 1.09, and then we would take it to the power of the number of periods, but this case it's just 1, so we don't really need to do anything. If we wanted to, we could put the caret 1 to show power of 1, but we're going to come back with the 6422 value. I'm going to put that down to 2 decimal places. But the way we can do that, just sticking with the theme of using Excel functions, is to use the present value function, use that discount rate of 0.09, and the number of periods is 1 because it's just 1 year. And that future value that we're going to receive in 1 year is $70. So the present value of $70 in 1 year, to be received in 1 year at a discount rate of 9%, is going to be, again, 6422. Okay, and then part B asks what's the amount of the investment 100 years, or what amount this investment will pay 100 years from now. So what's the 100th payment going to look like? Again, starting with payment 1 of $70, but it's going to grow 5% each year thereafter. So what does that 100th payment look like? So in this case, we're going to calculate the 100th payment, which would be a future value. And we're going to use a rate, the growth rate, which is 5%. So again, we're not discounting back. We are looking at what this $70 will be in 100 years, given the 5% growth rate. So we're going to use 5% as rate. The number of periods will be 100. And our present value is $70. And just notice that we are getting annual payments, so we don't want to confuse that with an annuity, because we are, in this case, just trying to figure out what that 100th payment will be, what that one figure will be, and that's starting out with a first payment of $70. So this is not an annuity problem. This portion, this part B, is just simply trying to figure out what that 100th payment would look like, starting off with an initial payment of 70. Okay, so the present value of that 100th payment is what? So if we go back to using the present value function, and we're going to use a rate of the, it's given as the discount rate. So we're back to using the discount rate to find the present value of that 100th payment. That 100th payment is out in the future, so that is our future value. I'm just going to reference it here on the sheet. And the number of periods that we're discounting back, of course, is 100. And so the present value of that 100th payment, that $9,205.09, is just $1.66. So if you think about that in the reverse, if we were to start off with $1.66 and we were going to earn 9% on that every single year for 100 years, it would grow on its own up to $9,205.09. And if you want to see that or prove that, we can do a future value calculation, and we would start with that present value of 166, and we would use that rate of 0.09 and 100 periods or 100 years. And you can see, just to prove it or confirm it, they will grow to 9,205.09. Okay, and then in part C, we're asked what the present value of this entire stream of cash flows is. And here we actually need to borrow from the Gordon growth model, which we will see and talk about a lot in chapter 7. But with that model, how we calculate the present value when we're dealing with a discount rate and a growth rate, and it's key that the growth rate is less than the discount rate. It's the only way for this model to work, is that we use the cash flow, the initial cash flow, year one cash flow, in this case the next year's cash flow of $70, and we divide that by the discount rate, which is 0.09, minus the growth rate, which is 0.05. So again, before I hit enter, this is what's called the constant growth model or Gordon growth model that we will see a lot of in chapter 7. But it's calculated by taking the next year's dividend or next year's payment, which in this case is $70 for year one, and we divide that by the difference between the required or discount rate, 0.09, minus the growth rate, 0.05 in this case. So we come back with $1,750. I'm just going to check that and make sure there are no decimal places beyond that. And there's not.